Okay, hello everybody, wherever you are in the world. My name is Panos Alexopoulos. I'm a data and AI practitioner and educator, and today's talk is going to be about the relation between RDF and label property graphs, which are the two main paradigms by which we represent knowledge graphs nowadays. I'm going to focus, the talk will focus on things to consider when we move from RDF models to label property graphs and vice versa. So, some more things about me. I've been working in the field of data semantics and NLP AI since around 2006, and since 2016, I'm head of ontology at TextKernel, a company that builds software for matching CVs and jobs. And my team there, I'm responsible for developing and delivering a large cross-lingual knowledge graph in the HR recruitment domain. I've been using RDF and Neo4j mainly for this, and so I have experience in this field for more than 10 years now. And in 2020, I published with O'Reilly a field guide, a book for semantic data modeling, where I focused on conceptual modeling issues, pitfalls, strategies, etc. Semantic data modeling is what I do. And by semantic data modeling, I practically mean the development of descriptions and representations of data that convey the data's meaning in an accurate, explicit, and commonly understood and accepted way among humans and systems. This is a definition that encompasses a lot of different artifacts, such as taxonomies, metadata schemas, vocabularies, and also knowledge graphs. Knowledge graphs have become quite popular, quite famous, mostly in the last decade, since actually Google rebranded the term and with its own knowledge graph that it's visible through its user interface. And we can say that the knowledge graph is practically a large network of interconnected entities and concepts under explicit and search semantics. And when it comes to building and representing knowledge graphs, there are two currently prevailing paradigms, two currently prevailing representation languages. The first and newer one is the label property graph model. This is a model, this is a representation language that Neo4j supports and implements, and it's quite flexible, as we will see, and quite easy to follow. On the other hand, we have also RDF and OL. RDF stands for Resource Description Framework, OL stands for Ontology of Language, and both these languages have been developed in the late 90s to early zeros as in the context of the semantic web vision, which is a vision for creating machine processable and interlinked data across the web. Both of these representation frameworks are used nowadays by different companies, and even sometimes within the same organization, with the same company, you have different teams using the two different paradigms, and therefore there is a need to understand more in depth what are the pros and cons and what are the particular characteristics of each, and how to be able to align between them. So I'll start first by talking a bit more in detail about the label property graph model. So in the label property graph model, the very basic element is that of a node, right? So we have a graph, and a node is the main element from which a graph is constructed. The nodes are typically used, to represent entities and concepts, right? So if we're building, for example, a knowledge graph about movies, we can use nodes to represent actors and to represent movies. The second fundamental element in the label property graph model are relations, or also known as edges. These are directed links between two nodes, always between two nodes, so they're always binary relations, and that also have a name. So, for instance, if we want to say that Tom Hanks has acted in Cloud Atlas, then we create the two nodes, Tom Hanks and Cloud Atlas, and we link them through a relation called acted in. The third component is labels, hence the name label property graphs. A label is a convenient way to characterize a node, to denote the node category mainly. So if we want to say, for example, that Tom Hanks is a person, we can put a label person in that node, on that node, and the same we can do for Cloud Atlas, put a label movie. Now, labels is very important to keep in mind that cannot be related to other labels, so there's no direct relation between. It's not possible to define a relationship between labels, nor we can define any properties about labels. Finally, we have properties. Properties represent characteristics of nodes and relations. So, for instance, if we want to have to model the date of birth, the year of birth of Tom Hanks, then we can create a property on that node called born with a value 1956. Or if we want to have the release date of Cloud Atlas, we can have again a property release with a value 2012. In addition, we can have properties about relations. So if, for example, we want to model which roles has Tom Hanks played in Cloud Atlas movie, then we define a property on the relation acted in between Tom Hanks and Cloud Atlas with the corresponding value. So if we put all this together, right, this is mainly what we have. We have nodes with their properties and their values. We have labels on the nodes, and we have direct relations, binary relations among the nodes with a name and with potential properties. And that's it. That's the main. This is fundamentally the label property graph model. Now let's see what RDF and OL is. In RDF, the idea is slightly different than the label property graph model. So what we have is triples. A triple consists of a subject, a predicate, and an object. Subject and objects are usually entities or concepts, and predicates are used to denote relations between those entities. So for instance, if we want to say that Alice knows Bob, then we have an entity, a subject, the subject Alice, a predicate knows, and an object Bob. The reason you see URL style here, names, is because RDF defines every entity formally as a URI, as a unique resource identifier. And the reason that it's HTTP-like is because in the context of the semantic web, we want to be able to publish those entities on the web, to have a resolvable name across the web. So it's a historical reason why we have in RDF this kind of unique identifiers. And the representation itself can be quite simple. There are many different ways to represent it, but the main representation is like a triple, right? So you can have simply a text file where you have every triple across each line, and that's it. So when you have multiple triples, as we see here, then practically we form a directed graph as well, right? So we can say that Alice knows Bob, Bob knows Carol, Carol knows Alice, etc. Now, what makes RDF also, again, very different from an LPG and quite much stronger with respect to semantics is a set of reserved vocabulary for describing entities and relations. So if you think of programming languages, right, when we learn a programming language, we know that there are certain words that are reserved for particular things, right? So for example, for the main function, or to denote the word float, to denote a variable that is type float, etc. Similarly, in RDF schema, we have predefined elements that have specific semantics and specific usage. So, for example, if we want to say that the entity country is a class, and I'll explain what the class is in a few minutes, then we can create a relation with a predefined name RDF type and link the country entity to a node with a predefined name called RDFS class. So RDFS class in this diagram, subclass of RDF type subproperties, so anything that you see in bold are reserved entities and relations, right? Reserved names for describing particular entities and relations. So RDF schema gives us a predefined vocabulary that we can and we should use in order to describe our knowledge graphs. Something that label property graph doesn't give you, right? And then we also have OWL, ontology web language, which is an even more sophisticated and even more complex modeling framework that adds additional reserved vocabulary for describing entities and relations, right? So here, for example, we can have a distinction between object properties and data type properties. We can have data types, etc. Now, the important thing to consider is that because of that, because the LPG model has fewer and less formal elements than RDF, transforming an RDF graph to a labeled property graph, and also vice versa, might lead to missing or wrong semantics. Let me explain this through an example. When we build ontology, when we build knowledge graphs, a typical distinction that we make is between classes and individuals. A class is a concept that represents kinds of things in the world that may serve as semantic types of other entities, right? For example, we said Tom Hanks is an actor, right? Or is a person. Person in that case is a class because it represents all the persons in the world, right? And Tom Hanks in that case would be an instance of that class, right? Similarly, you can say that we have the class building, and Empire State Building is a particular instance of that building. Dog is also a class, and lass is a particular instance of a dog. This distinction is fundamental and very common in RDF graphs. So in 99% of the RDF graphs that you might find out there, right, in any organization or even in public, you will see that there will be classes and individuals. Which means that if we want to transform, if we want to bring an RDF graph and represent it in Neo4j, for example, as a label property graph, we need to decide how we are going to represent the classes and the instances, especially how to represent the classes, because in Neo4j, in LPG, there is no notion of a class. There's no formal notion of a class. So, as I said, representing classes in RDF is done through predefined elements. We have a node, particular node called RDFS class, and for every class that we build, that we define, all we need to do is define the class and say it's RDF type class, and that's it. And then we can define instances of that class through the RDF type relation. And we can also define subclasses, like European countries, a subclass of country, through the subclass of relation. So the question now is, what do we do in an LPG for that? In an LPG, there are mainly two ways that we can do the same thing. One way is to do it is to model a class as a label, right? As we saw in the previous example. So if we want to say that Tom Hanks is a person, we usually put one option is to put a label called person and another label called actor. And actually, this is, if you see most of the Neo4j tutorials and LPG tutorials and examples, the main approach for representing classes is that of labels, right? So I would say it's 90% of the cases, maybe 95% of the cases that I have seen. Of course, we can always do something similar to what RDF does. So to have a node class, to take actor, for example, and make it RDF type class, and take Tom Hanks and make it RDF type actor. We can also do that, although unfortunately it is not usually done. So what are the problems and risks with classes as labels, right? So let's say that we decide to, when we import RDF in Neo4j, we decide to model all our classes as labels. The first problem is a semantic problem. A class can always be a label, but a label cannot always be a class, in the sense that when you have an Neo4j model in LPG, nobody tells you that this has the meaning of a class. A label is just a category. In theory, as a category, we can put anything we like, right? So for example, we can have a node and put something very abstract, which is not even like machine learning, for example, or some other characteristic that is not necessarily a class. A class in semantic modeling and in ontology is a much stricter idea, a much stricter notion, right? So when we transform RDF to an LPG, we are losing the strictness of the semantics of class by making it a label, right? Furthermore, if we just transform into a label, then we are not able to define relations and attributes for this class, right? So if I go back here, if in RDF I have the relation that an actor is a subclass of person, by making them labels, actor and person, I'm losing that relation. We don't have anymore the explicit relation between actor and person, something that we can do in an alternative way by using nodes and relations, right? Vice versa, if we have a label property graph with labels, and we transform this into RDF, we need somehow to determine whether its label is a class or is an individual entity. That's important, right? And this is not something automatic. We cannot say that every label is a class. Why? Because in its very definition, a class needs to have individual entities, needs to have instances. If it's not possible for a concept to have instances, then it should never be modeled as a class, right? So labels, because they have looser semantics and they can be anything, right? We need to be very careful when we transform them into RDF. A second case, a second example is certain axioms and inference rules that OWL defines. So in ontology web language, we are able to define particular axioms that govern relations. So for instance, we can say that a relation is symmetric. A relation is symmetric when it's valid in both sides. So for example, the sits opposite of relation is a symmetric property because if a person sits opposite of another person, then the other person also sits opposite of the first person, right? Like Tom sits opposite of Sarah, then we can infer that Sarah sits opposite of Tom. We also have inverse properties. So for example, if Tom supervises Julia, then Julia is supervised by Tom. And a third example is a transitive property. If Tom has office mate John and John has office mate Kim, then we can infer that Tom has office mate Kim. These kind of axioms are also very common in RDF and OWL models. In an LPG, these are not there's no mechanism for defining those. If we want to implement those, we need to make them in a custom way, maybe by means of code, on top of the graph, or perhaps by means of specialized cipher queries, etc. The thing is that if we're not careful, if we're not aware of this, then we won't be able to. We might lose them from a null model, right? And we would have to. We would lose some semantics there. We would lose practically these facts because we cannot really map them to an LPG. So, to wrap up, RDF and OWL and label property graph models are commonly used for representing knowledge graphs, but they are very different in semantic formality and nuance, right? RDF is more formal and more nuanced than a label property graph model. And of course, it's more complex. That's actually its con. Transforming an RDF-OWL model to an LPG has the risk of losing some of RDF's high nuance due to the LPG's low nuance elements. And vice versa, transforming an LPG to RDF-OWL has the risk of representing the LPG's low nuance elements with the wrong high nuance RDF-OWL elements. So we need to be careful on both sides, depending on what is our use case. Okay, so This ends my talk. Before I get any questions, I'd just like to let you know that if you are interested in further semantic modeling and ontology engineering, I'm giving a course next week with Dataversity on ontology engineering strategies and solutions, including RDF modeling, OWL modeling, and Neo4j modeling as well. So you are all welcome to join. Thank you very much. I'm open to questions.